So continuing with the design of timber structures, my today's lecture will be on the design of a timber beam. So the given numerical is the timber beam carries a uniformly distributed load of 16 kilonewton per meter. This is the uniformly distributed load, including its self-weight of the beam. The beam is simply supported at both the ends and the span is given, clear span of the beam is given, that is 5.5 meter. So we have to design the beam. So here the given data is clear span, we know it's 5 meter. We have to assume the bearing. When the bearing is not given, we have to assume it, and this bearing depends upon the clear span of the beam. Here we have assumed width of the bearing as 300 mm. So the effective span, first step will be to find the effective span of the beam. So the effective span of beam is equal to clear span plus bearing by 2 plus bearing by 2. So here the clear span is this 5 meter plus bearing is given as 300 mm. We will change it into meters, so it will come out as 0.3 by 2 plus 0.3 by 2. So this will come out as 5.3 meter. This is our clear span, effective span, sorry. This is our effective span. Now step second is to determine, we have to determine the bending moment, maximum bending moment. So step 2 will be determine the maximum bending moment. As you know that this beam is simply supported and it is carrying this UDL, uniformly distributed load over the whole span. So the formula for this UDL will be WL square by 8. W is the load on this beam, that is 16, into effective span is 5.3. So this will come out as bending moment will be 56.18 kilonewton meter. Now is the maximum allowable bending stress in the grain. Now this is the maximum allowable bending stress in the grain for inside location for deodar wood of standard grade. This is designated as sigma Cp. The value is 10.2 Newton per m square. This condition you can assume it, and this condition you will get from this design of structures, the code for design of timber structures, that is IS 833. This condition, the value you will get from this timber code. Now next step 3 is to determine the form factor. Step 3 is form factor for rectangular section. Form factor for rectangular section K3, that is form factor is designated by K3. So we have the formula for rectangular section as 0.81 d square plus 89400 by d square plus 55,000. So here we will assume d as depth of the beam, as here we will assume it as 400. So substituting the value of d as 400 square plus 89400. So on calculating you will get K3 as 0.9396. This is the value of form factor. Now maximum allowable bending stress. So the maximum allowable bending stress will be, since we have depth greater than 300, maximum allowable bending stress will be equal to K3 into sigma Cp. So maximum allowable bending stress, since our depth d, we have assumed d as 400, since d is greater than 300 mm, this is the condition, then maximum allowable bending stress will be equal to K3 into sigma Cp. K3 is equal to 0.9396 into 10.2, so it will come out as 10 point, 9.584 Newton per mm square. Now you have to determine the section modulus. Section modulus. We know the equation m by I is equal to f by y. Here we can determine m is equal to f into I by y, or f is equal to m by z. This I by y is your section modulus. I is moment of inertia and y is the distance from the centroidal axis. Or we can write as z is equal to m by f. So z is equal to m is your, so on calculating this value, m is your bending moment, that is equal to 56.186. it's in kilonewton meters, so it will be 10 raised power 6. Or maximum allowable stress is your 9.584. so on calculating you will get 5861.85 into 10 raised power 3 mm cube. So this is your section modulus. So beam is considered, now the next condition is that beam is considered laterally restrained, laterally supported if the condition is beam is considered laterally restrained if B is greater than span by 50 and B is greater than D by 3. So width of beam required will be equal to, B is equal to, span is your effective span, that is 5.3, that is in meters, we will convert into mm into 1000 divided by 50. So on calculating it will come out as 106 mm. So adopt B, we will take approximately as equal, B equal to 240 mm. Now you have to determine the modulus of section of rectangular beam. Modulus of section of rectangular beam, that is equal to modulus of section of rectangular beam, that is equal to BD square by 6. We had the formula as BD square by 6. So we have adopted B as 240 into D square. We don't know the depth, divided by 6. So it will come out as 40 D square. So 40 D square is equal to Z, your section modulus. 40 D square, we have the value of the Z as 5861.85 into 10 raised power 3. So this will, on calculating, this will come out as 382.81 mm. So adopt D as 400, approximately 400 mm. So D by 3 will be equal to 400 by 3, that will come out as 133.33 mm less than B. So our condition is satisfied. Now we have to check for shear. So we have to check for shear, check for shear. So you know the maximum shear force at the edge, maximum shear force at the edge of the support, maximum shear force at the edge of the support. You know, if we will make bending shear force diagram, it will come out as this will be your plus, this will be minus WL by 2, WL by 2, right? This will be your shear force diagram. So the value of the shear force will be, your load is 16 into whole span, effective span is 5.3 by 2 minus, we have to determine at the edge, bearing is your 0.15 into depth is your 400 mm into your load, that is 16. So on solving you will get 42.4 minus 8.8, it will come out as 33.6 kilonewton. So this is the value of the maximum shear force. Now maximum shear force in the beam, this was at the edge. Now maximum shear force, maximum shear stress in the beam, we have the formula FSH is equal to 3 by 2 V BD. So FSH will be equal to FSH is equal to 3 by 2. V is your shear force and the value is equal to 33.6. It's in kilonewton, we will change it into Newton, divided by B is your width, that is 240, and D is the depth, that is 400. So the FSH shear stress of the beam will be equal to 0.525 Newton per mm square. Now the last step is check for bearing. Last step is your check for bearing. Check for bearing. So reaction at the support, you know reaction at the support will be WL by 2. That will be 16 into 5.3 is effective span by 2, that is equal to 42.4 kilonewton. Now you have to determine the bearing stress. Bearing stress at the support, bearing stress at these supports, at the support, that is equal to shear force, maximum shear force, that is 42.4 converted into Newton, that is 10 raised power 3 divided by bearing into B. This will be 42.4 into bearing is your 300 and your width is 240. So it will come out as 0.588 Newton, 0.588 Newton per mm square. Now the safe working stress as per the code. Safe working stress in compression, safe working stress in compression perpendicular to the grain. This you will get from the code, that is IS 883 timber structures code. Safe working stress in compression perpendicular to the grain, the value is 2.6 Newton per mm square. Since this permissible value is 2.6, it's greater than the calculated value, that is design is safe, hence safe, our design is safe. So provide, hence provide a rectangular beam 240 into 400 mm dimensions. Thank you.